Welcome to Heavy Networking, the flagship podcast from the Packet Pushers Podcast Network, delivering you all the packets with no drops and no jitter. I'm Ethan Banks with Drew Conway Murray. And guys, I'm going to dispense with the rest of the intro that I normally go on about because I want to get right into this discussion with our guest. We are covering today how to prepare your cryptography infrastructure end to end for the post-quantum world. Your production IT operations are almost certainly using cryptography libraries that are not quantum safe. So unless you're a government agency, so secret you have your memory wiped every time you walk out the door like on Severance, that's probably not you as far as you know. So the time to begin planning a cryptography overhaul is now. But if you started to think about this, this is likely to be one of the most daunting projects you're ever going to be a part of because it touches absolutely everything. Clients and servers and apps and network devices, middle boxes, and so on. And once you start thinking the challenge through, it quickly feels overwhelming. Our guest is Richu Chanakashava from Palo Alto Networks, our sponsor for this episode today. And as we begin working through the challenge of implementing post-quantum cryptography with Richu, it becomes obvious that she has spent a lot of mental energy working through the complexities presented by post-quantum cryptography, as well as a framework for addressing those issues. So we're going to get into algorithms, a little bit of math, just a little, believe me, not the depths of cryptography, a little bit of math, capacity planning considerations when selecting ciphers and related topics like that. So listen to this episode for a head start on making your organization post-quantum safe. Unless you're already a cryptography nerd, you're going to learn about things that you didn't even know were things. So Richu, welcome to the podcast. And we got to start with some essentials. How does post-quantum cryptography deliver from the pre-quantum variety, the stuff that we're using today? Or maybe another way to put this, why are existing cryptographic algorithms threatened by quantum, and how does PQC address that?
Before I get into that, Ethan and Drew, thank you so much for having me. I am a big fan of the show for the last 15 years that I've already talked to you about. All right, let's jump in. Let's jump right in. So pre-quantum cryptographic algorithms, which you're referring to, are the RSA and the elliptical curve algorithms. So let's take RSA for an example. It works on prime number multiplication, but factoring those prime numbers and figuring out what those two prime numbers were is the challenging, complex mathematical problem. And that's why RSA was the choice of algorithm or cryptographic key exchange and signature algorithm for the last 30, 50 years.
That is, if I take two prime numbers, multiply them together, I get a result. Figuring out what the two numbers were that got me that result is a really hard math problem. And so that makes our current cryptography, pre-quantum cryptography, safe. So the point
it's a really
being,
hard math problem from a computational sense when the prime numbers that you initially took to multiply are very large, right? So that's where the computational challenge comes in, to reverse engineer and factor those two original large prime numbers is very difficult for an existing supercomputer or a classical computer. Now you take quantum computer, to your point, Ethan, this becomes certainly a child's play, or at least theoretically, with Shor's algorithm, we can prove that quantum computers can factor those two large prime numbers in the least amount of time. So it's from a theoretical sense, classical or supercomputers could take billions of years, and this is what the academicians say. But apparently, a cryptographically quantum computer can take a couple of days, which is scary, very scary, because 100% of today's internet applications support RSA, right? And maybe a good subset of them also support elliptical curves, which are based in discrete logarithms. And that is yet another complex math problem that we know that Shor's algorithm can also reverse engineer. So that is the threat.
You just mentioned Shor's algorithm there. Can you mention that, because it's kind of a pivotal point in my mind? It kind of separates pre and post quantum cryptography is what happened with Shor's algorithm.
That is correct. So asymmetrical encryption is what we are talking about, to get a little deeper into this. So RSA elliptical curve used for asymmetrical encryption, which is what the entire internet digital infrastructure relies on today, be it key exchange or digital signature algorithms and certificates and so on. Peter Shor in the 90s came up with this algorithm based on quantum mechanics that we knew at that time, that should a quantum computer become viable, his algorithm can be used to reverse engineer these complex mathematical problems. And who knew in the 90s that a quantum computer could become a reality? Nobody knew, because that we built this foundation of trust on the internet using these cryptographic algorithms. We didn't think about replacing them. We didn't think about building automation or agility into switching between algorithms. We trusted them. So that's where we're at today. And knowing that quantum computing has reached an accelerated, innovative space, that it has seen some viability in pharmaceuticals. For example, Cleveland Labs is working on customized antibiotics and so on, without getting into the depths of how quantum computing can become a reality and add value to our society. The negatives of that is that you could also build a strong enough quantum computer purpose-built to break RSA using Shor's algorithm. So that's where we are at today.
So is this all at the moment just theoretical, in that Shor's algorithm is sort of a potential to happen, or has someone actually used a quantum computer and broken a current, like a prime-based encryption algorithm?
There are some good research papers that have come out of the Europe, that have come out of China in the last couple of years, to prove that RSA-2K keys can be broken on a sufficiently strong quantum computers. And again, the strength of quantum computer is defined by the qubits and the stability of the qubits, as well as error correction. All of that has to get to a place where you have sufficient qubits. Shor's algorithm supposedly requires 1 million physical qubits, then mapped to some amount of logical qubits. So to your question, Drew, this is a possibility, that there is a definite possibility to build a parallelized qubit-based, significantly large qubit-based quantum computer. Now, when is that going to happen? When are we going to achieve that stability and that error correction to run Shor's algorithm? There are different answers, right? There's an answer by the academics, there's an answer by the analysts, there's now, based on the threat, a clear assumption by the different federal governments across the globe who say, irrespective of when, we need to act now. So, so to your question, Drew, there's no guaranteed answer that when a computer like this is going to be viable, but there is a very clear path to the viability of a CRQC. And today, Shor's algorithm is what is known to break asymmetric encryption. There's some concerns with symmetric, which is Grover's algorithm, is also another one built in the 90s that threatens symmetric encryption, but not in the way that Shor's does. So Grover's algorithm is more of a brute force method. I'm going to do trial and error to figure out if a certain hash function can be engineered or can be picked out of the many answers that I get using a quantum computer, versus Shor's, which is true reverse engineering to the source.
We're going to be throwing around a lot of terms. You mentioned CRQC, that's cryptographically relevant quantum computer, just in case that comes up again, and I'm sure it will.
Yeah. Okay. Another point about the timeline: we don't have a general agreement in the industry of when the timeline of when a cryptographically relevant quantum computer might exist with 1 million qubits. But I've seen speculation anywhere from 2029, just a few years out, to decades off, all depending on who's doing the thinking about it. But there seems to be a general consensus that within 10 years is plausible. Does that sound right to you, Richu?
Yes, I think the 10-year timeline is also coming from different compliance and mandates put down by federal governments. So if you're following NIST and commercial NSA 2.0 timelines, they say you need to start adopting the more safer cryptographic algorithms, which we'll talk about, which are the post-quantum cryptographic algorithms, PQC, as early as 2025 is what CNA says you need to start migrating to PQCs. In fact, NIST announced that they're going to deprecate RSA and elliptical curves by 2029, even disallow these two algorithms by 2035. Right. So, and then UK's NCSE standard body says by 2035 or as early as 2030 is when the migration should have been implemented successfully and should have taken to production. European Commission signaled by 2030 they're going to put together a quantum safe communication network. I think these are strong enough indicators to say the threat is real and you cannot wait. And that's why different federal agencies are putting down timelines from a compliance and an actionable perspective. Now, to truly answer the question, when is a CRQC going to be real, going to be viable? There's Gartner and McKinsey saying as early as 2027, 2029. Then there are academicians saying could be 15 years, 20 years. We don't know, but it's definitely going to happen. So it's that little bell curve. So the ones who are speaking the loudest about this are the ones who really fear the threat of data being harvested, which are the nation states, which are the government agencies of the critical infrastructures, the financial institutions of the world, right? And then there are maybe the others who may not see the threat as impending, but we'll talk about why you could succumb to it even if you don't feel the threat today. So those are different timelines driving this migration right now.
And 2030 isn't far away anymore. It seems like that. Oh, that's forever away. Yeah, that's like 5 years out. So,
I think you bring up a key point here. Why isn't 2030 so far enough? It's because of the sheer scale of the migration. We're talking about cryptographic migration. As you earlier said, Ethan, cryptography is everywhere. It's in your browser, it's in your VPN agent, it's in your operating system, on your laptops, it's in your application, it's in your Wi-Fi access point, it's on your little camera, your indoor camera that watches your cat, all the way to all the way to app infrastructure nodes, data stores, cloud service provider infrastructures, your private cloud infrastructure, your data center infrastructures. It is a fundamental piece to the internet, which is why we trust and rely on it to get to the internet in a safe and secure manner. So the scale of this migration is very vast. And that's why 2030 seems like tomorrow. That's why it feels daunting.
And the issue here is now that we do have cryptographic algorithms that we can migrate to. Here in the US, the National Institute of Standards and Technology has approved a suite of them. Can you talk about, some of the key ones and what they're used for?
Absolutely. I think we're going to talk about the key ones and the keys.
There we go.
So National Institute of Standards Technology, NIST, has been working on this project for at least a decade. That is the significance of how much work they've put in, as well as the academicians and the researchers have put in to submit newer cryptographic algorithms. And let's define them. So these are called PQCs, post-quantum cryptography algorithms. PQCs are not based in quantum mechanics. The moment quantum plays a word as a word in the name of it, feels like it's some sort of a quantum algorithm. It isn't. It isn't based on quantum computing or quantum mechanics. It's just based on new set of complex mathematical problems that we believe cannot be broken or reverse engineered or brute forced by a quantum computer, as well as, of course, a classical computer, the ones that we use today. So those are the net new algorithms based on newer set of complex mathematics. Now, NIST has standardized 3. There's a 4th and a 5th in order in the draft stage to get to the standards. The 3 are in 2 different categories. One is the key exchange, where MLChem is the final list that's been selected for key exchange. HQC is parallelly being put in as a second order standard algorithm there.
Also for key exchange?
Also for key exchange, yes. HQC for key exchange as well. So double-clicking on key exchange, this is a session that is established between 2 nodes that don't trust each other, which is your browser talking to a service or an application which it has never established a session with. That's essentially web application, internet-based PKI, public key infrastructure system, right? So for that key exchange, the MLChem or lattice-based key exchange mechanism is what NIST has put forward as a standard. Now, alternative to that was the HQC that we were talking about. Though there are these two new recommended standards, what we have to note is adopting PQCs is going to be moving away from a set of standards, RSA or elliptical curve, that have been vetted for the last 10, 20, 30, 50 years in case of RSA. And we're moving away from that to net new algorithms, net new library implementations, and sort of refreshing ground up from the operating system and these endpoint perspectives. So what the industry has decided from mitigating risk is to be able to approach this from a hybrid key exchange perspective. So we are going to retain a classical key exchange algorithm and concatenate that with a post-quantum key exchange algorithm. In case of MLChem, you will see hybrids being used, which are elliptical curve hybrid along with MLChem, and that's what the browsers have moved forward with. You'll see that being adopted in web applications. Same is true for your firewall providers like ourselves at Palo Alto and so on. So that is a risk mitigation strategy as this migration has been enforced, and we will stay in this world for the next 15 years, 10 to 15 years, until there's sufficient vetting of the PQCs, there's enough proof that MLChem has withstood the test of a CRQC, and potentially we will switch to a true MLChem. Now, I know I jumped off into talking about hybrid key exchange mechanisms.
Yeah.
I also want to shine light on the other standards from NIST, which are for digital signature algorithms, which are MLDSA, as well as stateless hash DSA, which used to be called Sphinx Plus. I still remember it as Sphinx. So these are two new standards, and a third one's in the works, which is Falcon.
I did a little reading on MLChem just to start to get a sense of, well, what's different about this for key exchange versus historically what we've used for key exchange. And the key seems to be lattice math. We're doing math with lattices. That seems to be the focus on a lot of the cryptographic algorithm changes that make them quantum resistant, if you will. Is that a valid observation?
That is correct. That is correct. And to your point, lattice math is supposed to be extremely complex. I know earlier in the call we were talking about how it introduces 100 or maybe a quadratic amount of dimensions.
Yeah, before we hit the record button. Yeah,
Yes.
As much as 100 dimensions, according to some of the watching and reading I was doing. Yeah. Okay, so we don't need to understand lattice math as network engineers, but I thought it was just an interesting note that seems to be what's changing in these algorithms that is making them cryptographically relevant, quantum computer resistant. There we go. We need to compress that. I guess that's why we're saying CRQC. Yeah. All right. So Richu, as we're developing a strategy then I'm assuming are we ready to talk about strategy, or do we need to talk about background stuff more? I was thinking we're ready to talk about a strategy to get us to a place where we're prepared for the post-quantum future.
Before we talk strategy, I do have one question. You talked about using hybrid key exchange for risk mitigation, and I just wanted to clarify what risks we are mitigating. Is it like, a dual stack IPv4, IPv6, just in case, the endpoint I'm trying to talk to doesn't support IPv6? Or is it that I'm essentially hybridizing this key exchange mechanism in case MLChem gets broken by is that the idea?
That's a great question. So there are a few different risks. So I'll highlight the top two. The first one is, yes, should MLChem be broken, we at least have, or should something in the library, the implementation of MLChem or the library that's been chosen for MLChem, because there are many libraries, right? So there is Open Quantum Safe, there's Open SSL, there is Wolf SSL, there's PQ Shield, there's one from Google, one from Cloudflare. So there are many libraries, and each of these libraries have different ways of implementing it. The algorithm is a standard, the implementation can differ. So based on how it's been implemented, there's a potential that one of these libraries has a weakness, which then sort of is percolated to every application and endpoint that's adopted this library. In order to mitigate those system-related risks, which are probable, highly likely, and highly probable for the next 10 to 15 years. You saw this in the early days of OpenSSL as well. So in order to mitigate that risk is where we are talking about leveraging PQC with an existing classical algorithm like an elliptical curve. Right? That is one aspect of mitigating risk. The second aspect is, of course, MLChem itself as an algorithm being broken. Because this is all theoretical proof to say that lattice-based math is not broken, at least based on Shor's algorithm. Lattice-based math cannot be reverse engineered. But there could be a third algorithm which says I can brute force lattice math. Just like Grover's does with symmetric encryption. Now, yes, with symmetric encryption, we are just doubling the size of the keys and saying that's good enough for today. Brute force is still not exactly engineering the solution. So we could land at that where MLChem, then we just double the key size or some recommendations as such. But if MLChem itself is broken, we want to mitigate the risk of data that's being encrypted by these net new algorithms. So bringing together a combination of a trusted known algorithm from a classical computer decryption threat perspective to a PQC, a net new PQC, which is the MLChem, and then suggesting that either way, we are sort of mitigating the risk from a classical computer decrypting or reverse engineering a key, as well as a quantum computer reverse engineering a key. So that is the risk we're trying to mitigate, as well as, of course, the library risks that I alluded to.
Thank you for that clarification.
So let's move into the strategy part of the discussion. If we're at a place as an organization where it's like, okay, we want to get ahead of this thing, we would like to be operating all of our cryptography libraries with post-quantum safe algorithms. What does that strategy even look like? You mentioned earlier, it was intimidating. You were like, it touches everything, the VPN, agents and the browser and wireless and et cetera. So how do you begin tackling this?
I think with a little bit of empathy for all of us. So we start there.
So
because
light your favorite scented candle, have a nice tea, and sit down with your documents. And
you need that one evening before you start on this journey, I think. No, I mean, jokes apart, this is truly one of the largest problems a network and a security engineer will try to solve or plan for, right? And I can go down the steps of how do you plan and get to a place where you start implementing a solution. But before we get there, messaging this to your executive leadership or to your board of directors is going to be critical from bringing the messaging back to your company's directives, right? Because the more we talk about when this threat is going to be real, the less you're focusing on the actual problem which exists today, which existed yesterday, actually. And we are masking the problem by asking when a CRQC. The real problem is that it doesn't take much skill to harvest encrypted data. It doesn't. It takes zero skill to copy or to steal encrypted data. We're not talking about sophisticated hackers getting into your infrastructure and then encrypting something and then doing a ransomware attack, or being able to authenticate as one of your employees. We're just talking about somebody sitting, accessing your Wi-Fi and potentially making copies of encrypted traffic all day. Somebody exfiltrating encrypted information from your data stores to an outside database without having to decrypt it today, without having the keys to even access it today. So it's the most simplest attack possible is copying encrypted data, with the thought that 10 years from today, 20 years from today, we are going to be in an industry where quantum computing has been converted to a service offering, has been converted to a commodity, sort of accessible to anyone with a pay by an hour opportunity. Why are CSPs, cloud service providers, Amazon, Microsoft, Google investing in quantum computing? There is a lot of business value in bringing quantum computing to solve complex other problems in the industry. So there is a business case to be made for when quantum as a service is going to be offered by the CSPs. So what I'm getting at here is all that a nation state or a bad actor needs to do today is make copies of encrypted data to be able to access it in the future. That is the problem we're trying to solve. So as long as data is using today's classical encryption, you've made it very easy for these attackers to make copies and know that they can get to that piece of sensitive intellectual property, trade secret, national secret, 10 years, 20 years from today, or even 5 years from today, depending on who's investing in this, right? So that is the problem you're trying to highlight to your board. And what that problem emphasizes is business continuity. 10 years from today, if your intellectual property is out on the internet or on the dark web, it's game over, right? 10 years from today, if you're a healthcare company and your PII data, your health records of patients have been exposed on the internet, the loss in trust with your healthcare facility or enterprise is fiduciary and congressional hearings leading to potentially a shutdown of the industry. So that is what's at threat. That's it. That's the risk that you're trying to mitigate. You're trying to continue, keep your business continuity, keep the trust with your public users, and make sure you successfully plan and migrate. And the success part is more operational because this is an operational challenge to migrate cryptographic algorithms across your infra.
So that's sort of you're recommending if I'm wanting to broach this project with leadership, that's something I want to highlight. That's a risk of why we need to undertake this project.
That is correct.
Okay.
More often than not, when I talk to customers, I realize that there's maybe 1 in 10 C-level execs who have potentially paid attention to or made this their top 5, top 10 priorities for the next year, next 3 years. And 9 out of 10 are still questioning the risk of it. So if you're a security engineer and you realize that this is more of an operational challenge, and you find it challenging to bring the messaging back to the CISO about, yes, operationally true, but like, why should we even undertake this and why now? This is your message to your leadership, right? And going back to your original question, Drew, now that I remember what the question was, apologies there. So how do you even plan? Because this is one of the largest operational challenge you'll go through. Is first, you potentially don't have even information or visibility into the cryptographic algorithms that are in use across your infrastructure. And the challenge with cryptography is your libraries at a browser could be running the latest, greatest, while your libraries at the application level were last upgraded in 2003, right? And they work just fine because guess what? Browsers are still trying to support maybe older encryption just to make sure that they're addressing and they're able to secure and establish sessions with all applications globally, right? So,
but there's systems in production today. Ask me how I know, where they're running cryptographic algorithms that are not safe, even by today's standards. They're crackable. There have been things broken. I worked for a company and we did a common sense security update on a reverse proxy that deprecated a bunch of aged out cryptographic algorithms that broke a bunch of clients that talked to that reverse proxy, because those clients were payment card terminals that no one touches. You don't mess with those. And therefore people couldn't swipe and get any kind of result anymore. So there's those scenarios too, where it's you're already insecure, let alone being safe in the post-quantum world.
That is very true. So there are I think that the biggest problem when you think about cryptographic operations around migrating cryptographic algorithms is that you still have systems, legacy systems, that are running SHA-1, that are running MD5, that are running older algorithms that were deprecated in the early 2000s or the 90s. You still have Windows 97 running somewhere in your infrastructure, which has an Active Directory, and you don't want to mess with it because your entire identity infrastructure, zero trust network architecture is built into your Active Directory. So challenges like those are probably going to be your biggest ones, where first identifying these legacy infrastructure nodes, your applications and your systems, all the way to then planning first identifying them. That's the inventory. The cryptographic inventory would be your step one, discovering and inventorying. And then you go into, where is my sensitive data? Like mapping your infrastructure to zeroing in on where the sensitive information is being exchanged through sessions or through VPN tunnels, transferred across tunnels, data center to data center communications, is the second big challenge that you're trying to solve for. And then the third one is, of course, figuring out who needs to play a role. Should I work with my firewall vendor to zone these legacy applications and systems and invoke a perimeter security which can do the cipher translation, which is one of the solutions that we just launched for this very daunting use case. Is I have legacy applications that I just cannot uplift or upgrade. How do I still operate in a post-quantum world?
Well, it's kind of like the IoT problem or any other sort of endpoint identification problem where, depending on the posture of that device, you treat them one way or another, depending on how that security posture assessment goes. This becomes another criteria. Well, what cryptographic libraries are you running? You're not running post-quantum safe encryption. I'm going to treat you like this as from a firewall policy perspective.
Correct. Exactly. So then it's one way is to, of course, continue to invest in modernizing your infrastructure if there is an option to do that. Now that brings us to another conversation which we'll have. But if there's an opportunity to modernize some of your infrastructure, you are looking at how to future-proof investments there, working with your vendors to do this from a 3-year, 4-year, 5-year perspective. But if you don't, and you still need to keep your infrastructure operational, you have to consider zoning them and leveraging a firewall or security node in order to still migrate that piece of infrastructure to post-quantum. Now, once that's done, you're also identifying other pieces of your infrastructure. Let's take end users. Let's break this infrastructure problem, daunting one, into three levels, right? It's the user side of things, the application side of things, and then your infrastructure or your network nodes, your network devices, right? On the user side of things, your IT team is heavily involved. It sort of is a simpler way to approach it, though it's more proliferated and less control. But there is a simpler way to approach it. There's a minimum browser version that you have to enforce. There is a minimum VPN agent version which support, and these are considering that both of these already support PQCs. In case of browsers, Google Chrome supports PQCs. The other browsers are catching up. In case of VPN agents, you'll have to work with your specific vendors to make sure that they support PQCs. And third would be your operating system. So if you have a Mac OS or a Windows desktop or something else, making sure that you're working with those respective vendors to upgrade the operating system to PQC library supported OS is critical. So that's the IT team's project for the next year or two, right? And then you're talking about the applications, the team who owns and secures applications. If you have private applications, which you build, host, manage, which is true for most enterprise companies, in those scenarios, you're working very closely with your application teams to put down security policies which enforce post-quantum algorithm libraries being supported. If you're shipping code tomorrow, this should be a minimum security requirement as part of your security profile being enforced, right? And you could have products to make sure that before a code goes from supply chain to commit to production, this is already being checked at the supply chain level, right? You're checking for code signing, you're checking for libraries that are supported, you're checking for older, vulnerable, deprecated algorithms which should not be supported. You're checking for all of that, not just PQC support, you're checking to make sure the deprecated ones are disabled or removed, right? So all putting those security policies in place is going to become critical for private applications. For SaaS, work with your vendors. Your vendors are the ones who you should be enforcing these policies to your vendors, to your suppliers, to your technology partners, right? So that's the future proofing of investment piece of the conversation.
Has regulatory compliance come in, like HIPAA, PCI, SOX? Have any of those standards begun to require PQC in order to be compliant?
Yes. So you see NIS2 playing a very strong PQC enforced compliance requirement in the EU. It's already there. Financial institutions are being regulated. In fact, there are timeline mandates as well for them to support PQCs. Here in the US, there is a CNSA2, Commercial NSA 2.0, which enforces it across code signing, web applications, network firewalls and load balancers, browsers, and so on. So there are very clear guidelines from timeline perspective. When do you start? When do you complete your migration? So these are already out there. So if you haven't checked them out in terms of timeline, I would strongly urge you to start reading through them.
So you mentioned the first thing is cryptographic visibility and inventory, and that's sort of easy to say, but a little harder to do. Do you have any advice or insight on where folks should start and where are areas that folks might not have been thinking about as they think about an inventory?
So there are a few different ways to inventorying your infrastructure. So one is cryptographic libraries that are supported across each of your network node, browser, VPN agent, firewall, application, etc. So these libraries itself, what library, what algorithms are supported by these library versions, so on. And then the second one would be where you have to actually then take into consideration what algorithms are actually in use by these network nodes. So browsers connecting to an application are using a specific algorithm based on what was exchanged or negotiated between these two endpoints. So one is what library is supported. Second, what algorithm is in use across the session. These two pieces put together is where you bring in the visibility and the intelligence of cryptographic weakness or strength across each of these nodes. We at Palo Alto do that through Cortex Cloud, which is our solution which brings in the library-rich information for all your applications. As I said, before it goes into production, we have all the policies and profiles to make sure you're checking for vulnerable algorithms that are in place to vulnerable libraries that are in place. And then we have the cryptographic inventory solution within Strata Cloud Manager, which takes all sessions into account, all the sessions going through your firewall portfolio into account and connects the dots, right? So bringing these two key pieces of information is where you get 100% information on cryptographic metadata that's in use.
Well, you're underselling it a little bit in that as I was digging through prepping for the show, what you guys just put out, you get a quantum view. That is, you can see all the, here's my understanding of this, tell me if I'm wrong. You end up with a view where you can see all the cryptographic libraries that are in use across your network and then where they come from in a unified spot. So you end up with this like inventory basically right in front of you of everything that the Palo Alto Networks infrastructure has seen. Do I have that right?
Yes, we make it simple for you. So let me shine light on the challenge itself. It's to conduct a cryptographic inventory, you need different agents in your network watching these sessions. Either that, or you need logs from all your network nodes being flushed into a single source, which can then give you a view into all the different ciphers across nodes and users. We do that for you natively on our firewalls today. You have zero effort on day one to even be able to inventory, right? Now, what we're doing is we're taking it 2 steps ahead. The firewalls are the network monitoring tools. We are bringing that maturity of information to a platform, which is the Strata Cloud Manager platform, and then helping you visualize where in your infrastructure do these vulnerable cryptography algorithm live, which user device is using it, which application is still using, which certificate is still running RSA 1K keys, or invalid issuers are certificates with invalid issuers, certificates that have been revoked. Simple details like this are critical, which are critical to your business continuity, is what we are reflecting from a comprehensive single source of truth perspective on our Strata Cloud Manager today.
Okay. So that helps with the all of the inventory, helps you with visibility. Now I get a view into what's actually running across my network. Another piece of this puzzle in my mind is hardware acceleration. That is, there's going to be a chip in a lot of my middle boxes that's going to be accelerating cryptographic functions. So as I begin adopting post-quantum cryptography, what do I do? How do I keep up with the hardware acceleration that's required so that I can get the kind of throughput out of my middle boxes that I need?
True. So that is where we kept this topic aside, and we are coming back to it, which is the future proofing of investments. So it's critical that if your leadership and you as an engineer, a network security engineer who's working with your vendors and perhaps putting in a purchase order today for some set of ZTNA agents or a set of subscription for your SaaS providers and so on. As you do that, working with your firewall vendors and so on, as you do that, you're just probably thinking about a subset of problems that you need to solve for the next 3 years, for the next 2 years. What should be top of mind in that set of problems is this vendor quantum ready and quantum safe? Does this vendor have a roadmap to be quantum ready and quantum safe? And now let me tie that to the actual hardware discussion that we are trying to have. Imagine purchasing hardware today which does not fulfill the quantum compute requirements or the post-quantum cryptographic compute requirements 3 years from today. That is going to be extremely expensive for you to go redo a refresh in 3 years from today. So this is the conversation you need to have starting 2025 to make sure you're future-proofing those investments into the far future. With Palo Alto's recent launch, with our Orion 12.1, we launched a Generation 5 hardware called the PA series, the 5500 specifically, which bring in that quantum optimized compute for post-quantum cryptographic algorithms. We have 256 cores, which is heavy, which is intense.
Yeah.
When we ran testing for encryption, decryption for SSL on this platform, and we compared it to RSA, we did significantly well. And I'm talking apples to apples comparison, because we already know that when it comes to the hybrid cryptographic algorithms in adoption, which are PQCs and elliptical curves, it requires 2 times the key share, right? These are larger client hellos. But imagine getting good and better performance when compared to RSA. So that's where our platform is quantum optimized from a scale and performance perspective.
One thing I wanted to call out is I think you mentioned the term crypto agility at some point during this conversation. And I think maybe if we're talking to folks about this being kind of a massive exercise, they also should be thinking of it. It's not really a one and done, because if somewhere down the line a library turns out to be vulnerable and needs to be updated throughout your environment, or MLChem or another algorithm proves crackable, you kind of have to go through all of this again. So it's not I guess that's what crypto agility is. Yes. Can you sort of talk about what that term means and how folks should be thinking about this?
Absolutely. So agility, you should think about agility in three different ways. One is you want agility in the algorithms itself. If you had to replace ML-Chem with a different algorithm, it could be HQC, it could be a third. Should ML-Chem be broken in that scenario, you should be able to do that in a seamless way. When I say seamless, one is you have to make sure that the operating system, the firmware, the hardware is able to support not just one PQC algorithm, but multiple of those. And that's the investment that you're making with your vendors today. Mm-hmm. So having that multi PQC algorithm support from the entire tech stack perspective is key. So that's the first level of agility. The second level of agility is automating cryptographic changes is a nightmare. I know from an operational standpoint, it sounds like the right thing to do. But imagine updating your proxies while your applications and browsers haven't upgraded themselves. So, so yes, enforcing and automatically updating is perhaps not the end goal you're trying to achieve, but from an agility perspective, centralizing your cryptographic policies is a minimum smart decision to make, because you don't want to change ML-Chem to HQC on a per node basis yet again. Today you're having to do that from RSA to ML-Chem. Tomorrow you should not have to do that for ML-Chem to HQC or ML-Chem to another. So centralize your cryptographic policies and profiles in order to make sure that these changes can be determined or can be framed in one location, and then perhaps enforced from a local team perspective. So at least having that key control, I think, would be a good start to a long line of fixing operationalizing challenges.
Man, I'm just, you said all that. And I'm like, yeah, that sounds wonderful, but wow, how are you going to implement that? That is going to be a challenge for a lot of folks.
And that's something that we try to make simple through our Strata Cloud Manager. So that's the other piece. When we talk about crypto inventory, we're not just talking about inventorying cryptographic ciphers. We're also trying to say that let us help you with centralizing your cryptographic policies and profiles. Now, how that then takes you to enforcement can be regional, can be based on a subset of firewalls, can be based on a subset of ZTN agents, and so on, right? So operationalizing it is a two-step process, but centralizing it should be at a very minimum. So that's what we try to bring as well.
Richu, this has been a kind of a mind-expanding conversation. Thank you. But we'll close on one more question. We've been talking about quantum security, quantum readiness as if it's just a task for individual enterprises, but it seems like this needs to be more of an industry-wide effort. Do you have a sense of what other actors or stakeholders people should think about being involved or getting involved to move toward quantum safety or quantum readiness, at least?
So this is an industry effort, a wide industry effort, right? So if you think about every tech partner that you work with, let's take Palo Alto, for example. We have hardware firewalls. So we work with chip vendors, we work with processors. So we're talking about NVIDIA, Intel, AMDs of the world, who also have to come together to build a post-quantum cryptographically accelerated chip in order to provide for the next era of cryptographically accelerated or scalable performant algorithms, right? So we're talking about the chip vendors there. Then everybody today is either in one cloud or multi-cloud. So you're talking about your cloud service providers, their infrastructure to be quantum ready from a post-quantum cryptography support perspective, but also accelerated as well as secured. So when we say CSPs bringing quantum readiness into their infrastructure and security, we're talking about their firmware and their software being code signed by a PQC, so it's tamper resistant, right? And then comes the big picture of the certificates. Certificates are ubiquitous today, especially with the explosion of IoT and IT. Certificates have have a proliferated access into the internet today. Digital signatures and certificates have to be replaced to post-quantum digital signatures, MLDSA or stateless hash DSA. And the PKI industry has a very big role to play. The root CAs of the world, the PKIs, the enterprise CAs of the world, who provide that certificate infrastructure to these enterprises or to our publicly trusted web applications, all of these certificates have to be renewed and replaced, right? And then we're talking about managed service providers or GSIs, the global service integrators, systems integrators of the world, who the Deloitte, Accenture, IBM coming together and helping us to this infrastructure upgrades. So I just mentioned a few, but this is a technology ecosystem partnership across the board for three things: for making sure you're interoperable, you're truly quantum ready, not just quantum safe, but quantum ready for the scale of it. And third is you're doing this at a timely manner. So you're working with each of these partners now.
Well, Richu Chanakeshava, I think I'm close on your name. Anyway, thank you for joining us today. This has been, as Drew said, a mind-expanding conversation. I learned about things I didn't know were things, and I don't know. I started going down the rabbit hole on all of these issues on YouTube and reading Palo Alto Network's blog posts that were explaining the problem and so on. It's like, oh man, there is so much to learn. There is a lot of information. Now, on the packetpushers.net site, you can find the show notes for this episode, and we will link to a couple of blogs by Palo Alto Networks explaining the challenge here, talking about Orion 12.1 and the quantum view I was mentioning, and so on. Richu, are there other links or places you want to send people, or maybe you want to share your LinkedIn, something like that?
Sure. Yeah. I'll put in my LinkedIn link for anyone interested.
Okay, excellent. We will, and we'll have those in the show notes as well, along with some other useful information that we found online from NIST and so on. And thank you for listening to Heavy Networking today. I hope you got something from this. If quantum, I don't know, a bunch of you that listen to the show are skeptics, and it's like quantum's far away. It's fairy dust. It's not going to happen. It's not going to amount to anything. But that does not seem to be what's happening. One of the recent headlines that's been hitting my feeds is about quantum computing being able to function in normal temperatures instead of having to be cooled to near absolute zero. Right. Well, that was one of the big barriers. Well, if that develops normal temperature for quantum computing, that puts it within the reach of many more organizations. So yeah, we don't have the million qubit system yet, but if that comes, I mean, and it does seem to be coming. It's real, and it's going to be real sooner rather than later. Within years as opposed to decades. Anyway, if you guys reach out to Palo Alto Networks to discuss quantum readiness, would you please tell them that the Packet Pushers sent you? We like to feed our families. And telling sponsors where you heard about them is the very best way to help us buy groceries. If you have any follow-ups for us, please hit packetpushers.net/follow-up and let us know what is on your mind. We're never going to make all of you happy. We know that, but we do try our best, and those follow-ups help us let us know how we're doing. I've been Ethan Banks, along with Drew Conway Murray. You can follow us on LinkedIn and Blue Sky, as well as the Packet Pushers Community Slack group. And last but not least, remember that too much networking would never be enough.